All right, good evening, everyone. You're listening to Prairie Pothole News. We are a weekly show here about hydrology across the prairies. And tonight we have Kelvin, Arshdeep, and Daniela coming to us from the University of Saskatchewan. They are going to tell us a little bit about their project on Pond 109. Hello.
Hello.
Hi.
Great. Yeah, so thank you for coming in tonight. First off, what can you tell us about Pond 109? What is there to say? What does it look like? Where are we?
Well, the Pond 109 is in St. Denis, a national wildlife area, which is about 30 minutes of the east of the Saskatoon. It is located near the Aspen Parkland and the mixed grassland ecoregion in the southern part of the Saskatchewan. It's basically a study area for the Environment Canada scientists since 1968, and they evaluate the consequences of the agriculture practices on the water flow habitat in the prairies pothole region.
Great. Can you just define a wetland for our audience?
Yes, of course. Wetland is a land which is covered by the water that provides a ranges of services. So wetland serve as a defensive system for the nature and the biodiversity by mitigating the downstream floods and through the water storage. It also acts as a pool of flux for the greenhouse gas, reduce flood risk.
Okay, so
Yeah.
most of our listeners are here in the prairies, so they would think agriculture is important. So what is the consequence of switching this wetland to agriculture?
I guess replacing a wetland into agricultural land increase the nutrient while removing the ability to filter them and also increase the flooding.
Okay, now nutrients, you were talking about phosphorus. Now that's naturally occurring in a wetland anyways, correct?
Yes, you're right. But we are altering the natural processes by draining the wetland and moving more surface phosphorus downstream. And when it accumulates, it causes algae bloom and which can cause anoxia condition and which is very bad for the wetland species.
Okay, so by draining the wetland, we're just moving phosphorus and water downstream and affecting downstream?
Right. We are reducing the water quality downstream, but we also have also have the economic impacts upstream. So replacing the wetland with agriculture will increase the productivity and the crop yield, but it also increase the flood risk, insurance cost increases, and the downstream farm experience the same flood risk as well as the phosphorus load. It also reduce the water quality, as this is all happening because of the upstream decisions.
Okay, so what specifically is the problem here that you're researching?
Yeah, we are basically focusing on what drives the phosphorus in and out of the pond and how this movement of the phosphorus affects the downstream rivers and lakes, and in what capacity can wetland drainage pose the flood risk to various wetlands and surrounding areas.
Okay, excellent.
Yeah.
Thank you. So Kelvin, how do you go about figuring something out about this problem? You've created a model, is that correct?
Yes, sir. But in order to understand what variables and parameters to change, first we need to understand the hydrological processes that characterize Pond 109, its watershed, and also what hydrological processes may be important in the export and import of nutrients. In this case, our model, phosphorus. The conceptual animation highlights the conceptual animation we see right here highlights the hydrological process in the prairie pond. We see precipitation in the form of rain and snow. When rain gets on the soil surface, some of it infiltrates and some end up as runoff. We also see groundwater movement in and out of the pond depending on the kind of pond. In winter, the snow that falls accumulates as snowpack on the ground, and during period of melt, the amount of runoff into this pond is greatly increased. This we will get to shortly as it dominates the hydrology of the prairie pothole region. Finally, when there is enough runoff to cause fill and
Okay, so how does this work? What's the hydrology in Pond 109?
with the data from class land surface scheme, we were able to analyze different hydrological inputs and output variables to understand these hydrological processes. The first things we notice from this figure are two big runoff events, likely due to earlier spring melts in spring 2013 and 2015, which end up influencing the height of pond as we see at these 2 points. When we compare this other figure to the previous one, we notice that precipitation and evaporation do not affect runoff in this area. Seasonality is the major driving force in the trends we notice for the figure on the right. When we look at the data for snowpack, we see a nice trend and a positive relationship with runoff. We notice that SWE and spring melt contribute immensely to the runoff and the height of the pond. When you go below the ground surface, we notice the soil water storage drives pond recharge. The more water the soil stores, the higher the chances of pond recharge.
Okay, that makes sense. Okay, so you're just virtually draining this watershed.
Yes.
Okay.
There were no water escaping the pond even during the big run of storms, but we dropped the threshold from 2.5 to 1, and boom, we'll be spilling.
Okay.
We see this in both figures, the left and right. And on the left, what we see is spill discharge being negligent, and on the right, we notice a spill for those runoff peak years.
Okay, and that's bad because then the water is flooding downstream?
Yes, that definitely moves more water downstream and everything in it, including nutrients. As you can see in the figure, we notice that as cumulative spill discharge increases, we also see a similar increase in cumulative phosphorus spill over time period.
Okay, we're talking about phosphorus again, or nutrients. Someone explain that. What is phosphorus doing here?
So in comparison to, say, the nitrogen or the carbon cycle, phosphorus is considered limited for productivity. Phosphorus in water is almost always in the form of phosphate. Some of the factors that control that availability in the wetlands include climate, soil type, landscape position, hydrology or drainage, which is kind of what we're talking about here today, along with soil chemistry. There's something called phosphorus internal loading. So that happens when phosphorus comes from those internal sources such as sediment in the wetland. And that can happen when that water column mixes and basically re-injects the phosphorus from the sediment to the water. Wetlands have a high sediment to water column ratio, so that basically means that they're very shallow and that they mix easily. In order to understand all these nutrient transformations in a wetland, we do need to look at some chemistry. So for example, redox potentials and soil type.
All right, redox, I don't know what that is. Can you tell me about that?
It's basically a chain of chemical reactions that can have a significant impact in wetlands. For phosphorus, those are closely tied to iron redox reactions. So basically with high oxygen, that iron can absorb phosphates. But on the other hand, if we have low oxygen, we'll see that phosphate in sediment diffusing into our water column. Basically, this internal loading of phosphorus happens mainly when you have low nitrogen to phosphorus ratios, when you have high organic matter, low oxygen content, high temperatures, high pH, and of course a high microbial community. So this is all very complicated stuff, but hopefully we can catch another episode, take a deeper dive on redox reactions.
You're welcome back anytime. So how do the microbes play into this? Is that why we see algae in the summer primarily? When they're hungry? I don't know.
Yeah, in the summer we have higher temperatures and we also have more light, which can increase that microbial activity. So in contrast, if we have low light conditions, that's going to decrease our phosphorus uptake. So simply because our algae is not growing as much within those low light conditions, the more available phosphorus we have, the more primary production there will be, and therefore those algal blooms that we're talking about. So the take-home message from this stuff is that in order to store phosphorus in our wetlands, we need iron-rich and oxygen-rich conditions.
Okay, this is incredible and a lot. Let's bring it back to something I understand. What is this ditch?
Ditches could be either tile drainage, where pipes are buried, or as culvert. Our model let us imagine spill threshold set at 1.1 to be drainage, so some water can be retained.
Okay. Did you mess with anything else?
Yes. We ran 2 scenarios and altered parameters for both. One focused on groundwater phosphorus interchange with the pond, and the other focused on pond and surface interflow to see how much concentration of phosphorus will be released from the system.
Okay, great. So you have your 2 scenarios, your parameters that you adjusted. They're both set to spill at 1.1 meters. Scenario 1, you increase the recharge bypass fraction, your phosphorus concentration in groundwater, hydraulic conductivity, and sediment thickness. All of this to essentially increase the role of groundwater phosphorus. And scenario 2, you increased settling velocity, phosphorus concentration in the pond and sediment, and you decreased pond radius, all to emphasize phosphorus in the pond. So what did you find?
Yes, you're right, but let me break it down. The first thing we notice is a drop in mass of phosphorus in the pond in both peak periods. This drop is compensated by phosphorus spilling out due to drainage. And also what we notice is an increase in phosphorus input from groundwater, which is due to the positive change in the BPF factor. Since we are adding more phosphorus to the system to groundwater, we are seeing an increase in P concentration in the pond. However, there's a rapid decline of phosphorus in the sediment, which could be attributed to increase in the thickness of the sediment, which in turn reduces the pore water to volume of sediment ratio. And since the pond is spilling and at the same time there's a rapid recharge by groundwater, we see a decrease in pond height and water table. In scenario 2, we make out initial phosphorus concentration levels in the pond to be positive, as opposed to the scenario without spill. The first thing we notice here again is the drop in mass of phosphorus in the pond, which is compensated by phosphorus export via spill. However, in this case, there is not a gain of phosphorus but a little amount of loss of phosphorus via groundwater interchange, unlike the first scenario. This means phosphorus only gets into the system via runoff and leaves via spill discharge. Nonetheless, decreasing the radius of the pond as well as increasing the settling velocity and the initial concentration of phosphorus in the pond leads to the increase in phosphorus concentration in the pond and its decrease in the sediment. Also, we see a little drop in the pond height, which is followed by a drop in the water table. The little amount of phosphorus lost to groundwater is an indication that not enough water is leaving the pond to recharge the water table, hence the drop.
Okay, so there's a lot to discuss here, but essentially, if we're looking at phosphorus mass exported, both scenarios have the same values, basically. Scenario 1, you had 134.5 grams. Scenario 2 is 133.3 grams. So with that in mind, is it safe to say that spill threshold, since it was the only parameter in common, is the reason we're getting these results?
For the most part, yes. Also, with the random parameters changed, it might be just down to coincidence. But these numbers highlight how much phosphorus spills when there is drainage.
Okay, so what else do you have?
We actually ran a sensitivity analysis in two parts. First, we created a contour plot that takes two range of parameter values as inputs, in this case spill threshold and phosphorus concentration in the runoff, to produce a model output, cumulative mass of phosphorus in the spill. This plot takes into account the various combinations of these sets of inputs to give various possibilities of the cumulative mass of phosphorus.
Okay, so this contour plot, it's really deep purple, and so does that mean that under most of these parameter combinations that phosphorus isn't really causing a problem?
Right on.
Okay, so when water has a high phosphorus concentration and it's allowed to spill because of the drainage ditch, then we see phosphorus export downstream.
Yes, sir.
Okay, so there's situations where there's no phosphorus exported, and that's this whole deep purple section of your contour plot?
Yes.
Okay.
We actually ran a time series plot to confirm that. The minimum values we witnessed were just zero for phosphorus concentration in the mass throughout the entire duration from 2013 to 2017.
All right. Well, what did you learn from all of this then? What are your conclusions?
Basically, draining a wetland by lowering the spill threshold is the only way the phosphorus escape out of the pond in our model. So it's the most important driver of the downstream effects, and the runoff is the contributing factor which making the P into the pond, while the spill threshold become the major dominant factor in the P export. However, as P is being exported, the discharge from the spill is contributing to the surface water downstream, which is making more flooding.
All right. Do you feel good about these results then? Is there anything you would do differently?
So Joey, there were some limitations to the model. The microbial community dynamics and the primary productivity components were not included. The physiochemical properties such as oxygen was also not included in the model, but is important for projecting that P export. Other additions such as pH along with iron and sulfate, both important elements and parameters of the phosphorus cycle because they can make that P available for uptake by plants. In our class model that Kelvin had described earlier, there was no parameter feasibility constraints, so that basically means no range in values that were provided, so that posed a little bit of a challenge when setting and justifying our parameter values. And lastly, for that same model, the runoff outflow did not factor in P spill, so that's our phosphorus spilling, in order to understand what other forces might drive that P export without drainage.
Okay, so what would you recommend?
The recommendation we made here are adopting the best management practices like the cover crops and manure management. Basically, we introduced like a 4R policies where the farmer can improve the nutrient management by applying the nutrient in the right amount in the right time of the year with the right method and the right placement. Whereas we have like a soil erosion control practices like no tillage agriculture as well, which mitigate the phosphorus transport into the downhill. And lastly, the use of vegetated buffer strip, which can be stripped along the river banks, which actually slow down the runoff.
Great. Well, thank you all for coming in today. That was a lot of information, but it's all available on your website. And thanks for coming in. We'll tune in next week for another episode of Prairie Pothole News.